Hello, students. Mr. Keister back with you again. Today we're I'm going to go through with you one of my absolute favorite labs of the year, and that is the one over freezing point depression. But more importantly, specifically in regards to making ice cream. Uh, this is a lab you'll look forward to doing when you come back. So hopefully that won't be too awfully long from now. Today is actually Monday, March 30th. But if you look back here, Chem 2 kids, this was the lab that we actually would have done on Tuesday the 17th had we been in school all this time as normal. And for you guys in honors, date would be a little bit past that. But anyway, this deals with freezing point depression, which is one of the colligative properties. Remember, colligative properties are those properties of solutions that depend on how much of a given solute you have in a given quantity of solvent, how many solute particles are there. It doesn't really matter what the particles are. It just matters how many of them are there. Now, we've talked about freezing point depression and boiling point elevation in our lectures, in our lessons over colligative properties. And so hopefully you're well aware of those by now. But the one thing I would would want to take from that in regards to freezing point depression or boiling point elevation is that, for example, water is a pure solvent, normally freezes at 0 Celsius or 32 Fahrenheit and boils at 100 Celsius or 212 Fahrenheit. But when you add a solute to water to form a solution, a lot of the water particles, your solvent particles, are then attracted to and tied to the solute particles. And when that happens, what ends up happening is with a drop in vapor pressure that extends in both directions that normal freezing and boiling point. So a solution then is going to boil at a temperature higher than 100 degrees Celsius, again, assuming the solvent is water, and the solution will freeze at a temperature below 0 Celsius. So the boiling point elevates, the freezing point depresses. So today's lab, we're going to deal with freezing point depression. In lecture, I mentioned that this is why we throw salt on the roads in the wintertime, because when you do that, you drive the freezing point of the solution you've made by dropping that salt on the snow and ice. You drop the freezing point to a temperature that is below the air temperature, which then causes the mixture to melt. And so and with ice cream, we have a very similar situation. Ice normally is at 0 Celsius, and that is not cold enough. I just noticed I have a cookie sitting here. Save that for later. Anybody notice that? Did you notice that I took a small bite out of it too? Sorry, couldn't help it. Anyway, ice cream actually freezes at about -2 Celsius. So packing, if any of you made homemade ice cream and you pack your ice cream mixture in ice, the ice is not cold enough to freeze the ice cream. So you get some nice ice cream soup, but you don't get the frozen product. So we add calcium chloride or rock salt, or I think in the store it usually is marketed as ice cream salt. You pour that on your ice, which will then drive the temperature down, which will then make it much colder, which then allows for the ice cream to freeze. So let me pull up the assignment here behind me. There we go. Okay, and we'll unfreeze that. So this is the lab sheet for Lab 10-2. So basically, I'll show you what we got here. What I will have for you, or had for you, made up in advance, is a little baggie here. It's got 3 teaspoons of sugar in it and 120 mLs of milk. Those of you, by the way, that are lactose intolerant, I have had this lab before using Lactaid or some other, lactose-free milk product instead of milk, and it comes out just fine. So no worries there. Anyway, I then asked you to add some flavoring to yours. I myself like chocolate, so I'm going to put a little chocolate syrup in there. Not too much, though. I always tell everyone, you can always add more later, but if you get too much in there, and it's too chocolatey or whatever the flavor you use is, then you can't pull it back out. So I'm going to kind of burp the bag here and get all the excess air out of it, like so. And now I'm going to mix it up like this. And so now we can see I got a nice chocolatey mixture there. Okay, now, next thing we're going to do is going to take the large baggie and fill it with 5 cups of ice cubes. So I've got that right here. There's 1, 2, 3, 4, and 5. Like so. Let's take the temperature of that real quick. That's something we got to record. I'm assuming it's close to 0. So I have it in there. And lo and behold, there she goes down. We're right at 0, actually. It's fluttering between negative 0.1 and 0. So close enough. All right. So that I would record right here. The initial temperature of the ice only is 0.0 degrees Celsius, since our electronic digital thermometers go out 1 decimal place. We also need, I may as well do that now, take the initial temperature of the ice cream mixture before we freeze it. So I'll do that real quick. Just open this back up. Put that in there. See what we get here. Of course, it's not frozen, so it's definitely going to be above 0 Celsius. And indeed, it is settling in at about 10 degrees. So I'll close this back up and record that. 10.0 degrees Celsius. Okay, so now, next I'm going to add to the 5 cups of ice 2 cups of rock salt. So this is our solute. I got 1 cup ready here. So I'll dump that in there. And 1 more. Excuse me a second. I don't know if I'm off screen or not. And there's the second one. And so then I'm going to take the baggie of ice cream and put it in here and close this up. Definitely going to put on the old gloves. I do not want to be holding this bag without protection over my hands, because I'm telling you, this thing gets extremely cold, extremely fast. So now I am just going to work this around for several minutes. What is happening is the rock salt is now mixing with the ice. The temperature is going to go down quickly, all right? And what's unique about this, or what's kind of interesting about this, is as the temperature is going down, the ice actually begins to melt. I don't know if you can see it, but it's already started to melt. Very odd scenario. So because what we're ending up with here is a water, or salt water actually, solution that is at a much, much colder temperature than what normal ice is. Very unique situation. Remember, pure ice is right at 0 degrees Celsius, but this ice and rock salt mixture is at a temperature much lower than 0 Celsius, and yet it's beginning to melt, which is exactly what happens on the roads, and that's what we want to happen. Even when the temperature is really, really cold out, we're able to melt the ice by creating a solution by dropping rock salt on it. A lot of times they drop sand on the road too, and that'll also, excuse me, That will also help drive the temperature down. But the main reason in putting sand in that mixture with the rock salt is for added traction for your tires to help with the slipping. I can tell that my ice cream is already starting to freeze. And it's only been a couple of minutes. This bag is so cold, I can feel it through my gloves. I actually, years and years ago, I had a student who thought he'd be the tough guy and try and do this with his bare hands. And I said, don't even think about it. You could get frostbite. And I was serious. Well, as I had my back turned and was dealing with, I think, some other students had questions or whatnot, I turn around. He's got the bag in his bare hands. And the kids were all kind of yakking about it. And I said, put that thing down. And when he did, his hands were like pure white. I mean, all the blood had drained out of him. And he said, I had no idea it was that cold. I said, well, I tried to tell you. But thankfully, he didn't do it long enough that he could cause any frostbite damage to his hand, because that easily could have happened. All right. Well, I'm getting close here. Definitely getting close. Because my ice cream is definitely not a liquid now. But I don't like it too awfully frozen. I kind of like it, not where it's hard as a brick. A little easier to eat that way. So I don't want to leave it in here much longer. I think I'm done. Good enough for me anyway. All right, so 2 things. Oh yeah, definitely frozen. All right, so first things first, got a couple pieces of data I want to take here. First is the temperature of the ice cream itself. Remember, ice cream freezes at about -2. I'm going to assume it's a little bit colder than that, and in fact it is. It's actually about -3.0 degrees, -3.0. Now, let's check the temperature. That looks pretty good. I would love to lick that off, but probably shouldn't. Now let's check the temperature of the rock salt and ice cream. As you can see again, whoa, that's cold. The ice is melting. But again, let me tell you that even though that ice is melted, the temperature of that is way colder than what ice normally is. So let's see what it is. Oh, it's shooting down in a hurry. Got down to about -12.5, but that's coming back up a little bit. Let's go -12. -12.0 degrees Celsius. So, here again, even though we have ice that's melting in there into liquid water, it is at a temperature that is actually 12 degrees colder than what pure ice normally is. All right. I'm not quite ready to eat my ice cream yet, although it sure is tempting. I want to talk to you about the calculations here a little bit. So, let's see here if I can scoot this down. Sorry about that. Got to lean over here. Well, that didn't do what I wanted it to do. Sorry about that. There we go. That's better. There we go. Okay, now, so first of all, at what temperature does water normally freeze or ice normally melt? And of course, that would be 0 Celsius. What was the final temperature of our ice and water salt mixture? That ended up being minus 12.0 degrees Celsius. So you can see then that the change in the freezing point then would be 0 minus negative 12.0 or 12.0 degrees Celsius. Letter C wants us to calculate the molality of our ice, water, and rock salt solution. Here's one thing you got to remember, and that is the Van Hoff factor or the I factor. Rock salt is calcium chloride, or ice cream salt is calcium chloride, and calcium chloride is an ionic solute. All right, it's an ionic solute, which means that when it dissolves in water, it breaks apart or ionizes into ions. And for calcium chloride, when it's dissolved in water, it forms a calcium ion and 2 chloride ions. So it breaks apart into 3 particles. And so its I factor or its Van Hoff factor is 3. All right, is 3, not 1 like a non-electrolyte solid would be. This is why we use rock salt to make ice cream or to salt the roads rather than sugar. Sugar would work just fine. The only thing is sugar is a non-electrolyte. And so when it dissolves in water, which it does because it has a polar end to it, when it does dissolve in water, it still remains as sugar particles. So when a sugar dissolves in water, it only dissolves into 1 particle in solution, whereby an electrolyte solute such as calcium chloride forms multiple particles. And so the effect on the freezing point or boiling point then is multiplied by that I factor. So in calculating the molality of our ice and rock salt solution, the change in the freezing point temp is equal to Kf, which is the freezing constant for water, times the molality of the solution, times I. All right. Again, if this was a non-electrolyte solute, then I would be equal to 1. We talked about that in our lecture. And so that would not play into this. But with I being equal to 3, it's going to alter the effect on the freezing point 3 times as much. So again, we'll plug in our change in freezing point, which was 12.0, not negative 12, but 12.0. Kf for water is a constant, 1.86, times m, which we're trying to find m, and then I is 3. So what you'll do then is solve for the molality of our solution. And then in questions 2 and 3, I asked you to explain what happened in regards to the ice cream in terms of colligative properties. And then provide another example of when we would use freezing point depression in real life. So make sure that you complete the lab handout, finish the calculations, answer the questions, and then make sure you submit this to me for grading as I have outlined now. I did that earlier today, actually, as I've outlined in an email I sent to you guys regarding how to submit graded work via Canvas. So with that, let's take a little taste here. I mean, I don't like, my mother taught me not to eat in front of people. And so I have a little bit of guilt here, but not that much. So look at that. Now that's the kind of ice cream I like, not hard as a rock where I can actually chew it. And oh my, that is some good stuff right there. Made even better by the cookies I brought with it to eat with it. Can't wait to have you guys back to do this one because I'll do it with you. Excuse me, getting all choked up. I'll do it with you again. So that's freezing point depression. In this case, we used ice cream as our example. That's it for today's lesson. I'll catch you next time. You guys take care. I miss you all. And hopefully we'll see you soon. This is Mr. Keister signing off.